So we looked at some cables, talked about ampacity, talked about twisted and solid strand wire, talked about the different conductors, which we basically already talked about. Talked about the American wire gauge. Uh, Talked about circular mills. Are you okay with circular mills? They're okay with circular mills. And then the circular mill area or the square mill area, you take the circular mills and multiply it by what? 0.785. We know the difference between the insulator and the jacket now, right? Are you okay there? And we looked at different types of jackets. We looked up the makeup on the typical low voltage cable. Now sometimes it don't have a jacket on there. Sometimes the insulation and the jacket are the same, right? You understand that? Then we looked at a medium voltage cable, which is what we have a perfect example over here. Talked about stress, talked about the makeup, and then what we need to do now. Coaxial cables. What we do when we get into communication cables, to understand that, is we have several characteristics about communication cables. So what we need to do here is we need to look at, learn about decibels, or dB. We all probably heard the term, but a lot of people don't know what it means. First of all, to understand communication cables, we have to understand something called impedance matching, or the characteristic impedance of a cable. And then we'll come back to this, if I can get it to load. So here's some of our power formulas. Y'all had all had DC, right? Or intro, are we okay? And y'all talked about power. What is power? What is power? What's power? What is power? Well, in electrical, what's the layer? Power is the same. It's work. What's work? To do work, you got to have two things. You got to have what? What's the formula for work? Yeah, there's the formula for work. Force times distance, right? So to get work, you actually have to apply a force, and then what's a force? That would cause or tend to cause something to change directions or move, right? You understand that? Go ahead. Yeah, so, well, no, the voltage is the pressure, but you can't have a force unless you have a pressure, right? So to create force, we have to take a pressure and we have to push it against something. As soon as I take that pressure and push it against something, we create a force. So the force would be more like the actual voltage drop, the actually doing work, right? But we call it a difference in a pressure, or it's a pressure, but we have to have a pressure before we create a force, and we have to have a force before we do work, right? You understand? So a force is anything that would do what? Would change or tend to change the direction or motion of something. And it's basically equal to what? Force times distance. Now, when we talk about power, power is a way that we rate how much energy is actually consumed, right? You understand that? And it's equal to force divided by distance. Okay. So that means if you create a force and you do it over a shorter distance, then you do more work. If you take that same force and you do it over a longer distance, you do less work, right? Does that make sense? Of course, if you know that distance and speed are inversely proportional to each other. So another formula for for power, is force times speed. And that's the one we use. So our voltage is our force, right? We use it as the force, and then the electron or the current flow is when we use the speed. And then we have several other formulas that are derivatives from that because of Ohm's law. So Ohm says that V is equal to I times ohms. So if V is equal to I times ohms, then what we can do is we can come down here and substitute I times ohms, right? You understand that? And that would give us I square R. Does that make a difference? Or I square ohm. Now, why we use ohms here is a lot of people don't understand that we have two types of opposition in an AC circuit or a communication. So communication, everything is changing, right? You understand that? So that means communication, even if it's digital, it acts like AC because it's constant change. And then this is where we add that thing we call impedance, where we add reactance, which these are the devices that vary with frequency. Are you okay? So we have, in all opposition in a circuit is rated in ohms. So reactance is rated in ohms. So what is reactance? Well, reactance is opposition that varies with frequency. Ohms is opposition that does not vary with frequency. So 100 ohm resistance is 100 ohm of resistance, whether it's in an AC circuit or whether it's in a DC circuit. Right? And so, like I said, these reactive devices do no work. So basically, this would be what we call apparent power. Are we okay? Everybody okay? So true power or real power would be equal to apparent power times something that we refer to as the power factor. Communication conductors are used to deliver power, communication, signal, or both. Most of the communication cables that you're going to run into are nothing but communication cables. They deliver signals, right? Similar to power delivery system, electricity sending information requires two electrical conductors. The DC circuit, the opposition to the current flow is set by the resistance of the source and the return conductor. In AC, which is what signals are, right? You understand that? Then it's set by the resistance and the reactance, or the impedance. Impedance is the opposition to the flow of AC that contains both resistive and reactive devices. But we always have that in cables, because cables always have resistance, right? You understand that? So all we're doing is adding the reactive component. To some degree, everything opposes the flow of electrical current. We talked about this, regulated power supplies. Regulated power supplies appear to have no internal resistance. Because what happens is when you load them, they automatically put more energy in to try to maintain a constant output, right? You understand? And these guys will get you. So if you short out a regulated power supply, then it's going to raise that energy up as high as it possibly can before the voltage drops down, right? You understand? And this is what gets us in trouble, because when the wire starts heating up, its resistance goes up. The regulated power supply just adds more energy because it's trying to get back up to its regulated value. Does that make sense? Yeah, so these regulated power supplies, these guys are the ones that burn stuff up. So the resistance goes up, the voltage goes up. The resistance goes up, the voltage goes up, and it pumps it into that short, it'll burn stuff up. An internal impedance causes the voltage provided by the source to drop when the load is attached. Power is work, not current and voltage. The primary goal of communication channels is to get the maximum power transfer from the transmitter to the receiver. Y'all understand that? So if a wire has impedance and a wire has resistance, then that means that's going to affect the communication channel itself. And our ultimate goal is to get the maximum power I possibly can from the transmitter to the receiver. Power transfer between the transmitter and receiver in a circuit is maximum when the impedance in the circuit, when all the impedance is in the circuit. Every signal transmitter has some impedance that is what causes the output voltage of the signal to drop when they're connected to a load. Example on the next side, and what we're going to do on this one is we're going to use resistance. because y'all have had DC and y'all understand. But what you got to do is we can replace this resistance with impedance, right? And what we're going to do is we're going to change the load resistor between a 10 ohms, 100 ohms, and a 1K. What we're doing, which of the following load resistors would you think would deliver the most power? Now, what we're doing is our load, and we're simulating the signal, the resistance of the signal source. And it's an AC signal source. So we're saying this signal source has 100 ohms of internal resistance. Huh? Well, let's think about it. Okay, so let's go and look. So this is the three sides. So the input resistance of the voltage source is 100 ohms. And what I'm going to do is I'm going to come out here and I'm going to use these three resistors. Now you can go in tenths of ohms, you can go in milliohms, you can go anything you want to, but we're just going to go through three resistors to understand what's going on. So if I've got a 100 ohm internal resistance, which one of these would you think give me the maximum power transfer to the load? So these are the loads I'm going to put out there. Which one would you think? The 10 ohm, the 100 ohm, or the 1000 ohm? Huh? Well, Charles says the biggest one. What do you say, Travis? The what? The 100 ohm? What do you think? Okay. Well, let's see. So what we're going to do is we're going to calculate how much power is getting to the load. Okay, y'all understand that? So the signal source itself has 10 volts. And of course that's going to be dropped as soon as I load this down, right? You understand? No, we're going to put another resistor out here. So I'll come in here and I put the 10 ohm resistor out here. And what we're trying to do is calculate the power getting to the 10 ohm resistor. Okay. So it's just a series circuit. What we like to use is we use a formula called, and what's nice about it is you don't have to calculate current. It's called the voltage divider formula. Are y'all familiar with the voltage divider formula? Like this guy's neat. We use it in solid state all the time because all in solid state, when we buy solid state devices, we're interested in the voltage that's at a certain point. And so what we can do is so the amount of voltage this resistor drops is relative to these two resistors. So the voltage divider formula says I can calculate any voltage. It's called VRX. So this is whatever resistor I want to drop it across. This only works in series circuits because that's when we get voltage dividers. And this is going to be RX over RT times VS. Now what's so slick is once you find that ratio, that's the same ratio that resistor will drop no matter what the voltage is. So if I said, and what people learn in DC, I said, okay, how much voltage would the 10 ohm drop if you had 15 volts applied? And I said, how much voltage would it drop if I had 30 volts applied? What most people would do would recalculate current. You'd recalculate current, but you don't. Once you find this ratio, this resistor will drop this same ratio no matter what the voltage is. So in this situation, I would say what? I would say VRX would be equal to 10 divided by 110, and then I would just multiply that times 10 volts. So what's VRX equal to? Or the 10 ohms. This is, we'll just call this RX right now. So you got to have y'all's calculator out, right?
It's a graveyard the other day.
Oh, that's good.
I had that when I was in high school, so I was one more.
I don't think I've got anything I had in high school, except my yearbook. I got my yearbook. So what we got, guys? Really? I didn't think it'd be that. Calculate this too. What's that? Yeah. And you multiply that times 10. And what we was talking about, that's the ratio it always has. Whatever ratio you got, whatever ratio you came up with, that's the ratio it always has. So you came up with what? Point. So 0.91. Now, once we got that, then I know the voltage. I know the resistance, so instead of using that V times I, what we'll use is we'll say power for Rx would be equal to V squared over R. So you can just take the answer you just got and square it and divide it by 10, and that'll give us the power. And that's what we're trying to find is the power that is getting to our what? To our 10 ohm resistor. So what do we get? So 9.01, so it wasn't 9.009, was it? So I came up with 9.01. So when I did all the math, it comes up and gave you 82 milliwatts. Are we okay? Pretty close to it? Yeah. So you just take your answer, whatever answer you got, and you just square it, hit your square key on your calculator. What's that? 0.909. So 0.91 would be okay, but this is okay. 0.91. I can change that. Oops. .082. The milliwatts is right? Okay. This right here is a little wrong. Yes or no? I'm listening. I don't want to do this right now. So wait a second. So let me bring up my calculator. I think I got it up already, right? So 10 divided by 10, Rich, divided by 110 equals that. Oops. Oh. Yeah, so this would be 910 milliwatts, right? Is that right? Millivolts. Is that right? I'm going to tell them how many times I've taught this chart. And then I'm going to square that, right? And then I'm going to divide that by 10, which comes up and gives us 83 milliwatts. That's 83 milliwatts, right? Huh? I don't know what's, so, 82 milliwatts. What we're going to do is we're going to pop the 100, the in out, and we're going to come up here and we're going to slide the, where was that? Okay, here we go. So we're going to slide the 100 in there. Somebody move my projector. I guess I did that. So what would be the power for 100 ohm resistance? Huh? No, it's the sum. So it's going to be 100, right? You understand? Divided by 200, right? Because it's the sum of the two, Charles. So I can do that. That's 0.5, right? And then we square that and divide it by 100. The one we're trying to find the power across. And what do we come up and get? 205, oops, 250 milliwatts. We're okay? So 100 ohms, 250 milliwatts. Then we come over here, we're going to put the 1,000 in there. So let's calculate it with 1,000. So it's going to be 1,000 divided by 1,100, right? Times 10. squared divided by, of course I might have got this wrong too, guys. Are we okay? So what did y'all get on the power here? Huh? So 22.6 milliwatts. Should have came up with the same, almost the same answer as the first one. So when did we get the maximum power transfer to the load? When the opposition of the load matched the opposition of the signal. And we refer to this as impedance matching. So in a communication channel, what I want to do, instead of arbitrarily choosing a opposition, we set the opposition in the channel. So if my transmitter, if I'm dealing with a 75 ohm system, my transmitters have 75 ohms, my cable has 75 ohms, and my receiver has 75 ohms. If everything in the system matches, it means I get maximum power transfer from my signal source to my what? To my destination. Y'all understand that? So we have these cables. We have a 100 ohm cable, which is what the Ethernet cable uses, 100 ohm cable. The cable that comes in the back of your TV is 50 ohm cable. It's RJ57, I think. What's that? Now speakers are different. Speakers is a bunch of power. Speakers is power. So those cables, even though they're AC, those are power cables. Because that's what they're doing. They're sending a ton of current. In a communication system, we don't send a lot of current. We send signals. So yeah, so speakers, but you're still exactly right. It's just that the wire is, we don't include the impedance of the wire because we just use basically, what do they call it? Duplex, twinplex, or what? Wire. But you have to match your speaker to the output impedance of your amplifier. But your output impedance of your amplifier on car stereos is like 2 ohms. House stereos is 8 ohms. So you don't want to go in there and hook up parallels and speakers in parallel, because as soon as you do what? You get distortion. Why? Because now you can hook some speakers in series and some speakers, but what you're trying to maintain is when you look at the specs for your radio, it's going to tell you the output impedance of the radio. And that's what you're going to do with your speakers. You're going to hook some of them in what? Series. Now the voltage is going to be shared, but the sound quality is going to be better, right? Because you keep it speed. Yeah, you've heard these people before. They'll be playing their radio and they play it real loud and it's all crummy. It's got all that distortion. And either they're overdriving their amplifier or the impedance of their speakers is not, and the amplifier is not. But in communications cables, these are high impedance loads, right? We don't want much current to flow in that because that would require a lot of power. Well, it's kind of, what you got to understand, impedance is set at a certain frequency. So the impedance of the cable is going to be given at a certain frequency, usually 1,000 hertz. So a 75 ohm cable would have 75 ohms at 1,000 hertz. And you're right, because if the hertz goes up, depends on how it sets the impedance. Usually it's not that bad, because what they do is they combine inductors and capacitors. So if I combine the inductors and capacitors and the frequency goes up, the opposition of the capacitors go down, but the opposition of the inductors do what? They go up, and it compensates for that. It's really, really cool. So this coax cable, that's what they're doing. They're setting up series inductors and then capacitors. Twisted pair cable, we use what they call twisted pair cable. And what it's doing is these wires are twisted together, and then you set up capacitors. The twist is your inductor, and then the what? Then the connection between the two wires would be the capacitor. So that's what we're doing. We're combining inductors and capacitors with a certain twist per inch and all this kind of stuff to set the impedance of the cable. Now on coax cable, it's the spacing. It's that insulator between the inside conductor and the outside conductor that they call the shield. So that spacing right there sets the capacitance, right? Huh? Yeah, that plastic in there, that insulates. Now, what we do is, a long time ago, when they started talking about hearing, they came up a method so they could calculate how the ear responds to sound, and our ears are nonlinear. So they came up with a method called dB or decibels, but it deals with what we call logarithms. Now, back in this gets people scared. They talk about logarithms, right? And they say, "Oh, logarithms." But what is a logarithm? So y'all have heard of logs before, right? I'm sure. Huh? Huh? Well, in AC, so when we start dealing with decibels, we're dealing with hearing ranges, but we also use dB in any communication system deals with dB because we're sending signals, and that's what sound is, right? But it's going to be modulated signals. So when we start talking about losses in a communication system and a signal, they're going to be dealing with dBs. But what we learned in AC, or what we learned in DC, is we use what we call what do we use engineering notation for? Well, why do we use engineering? Yeah, what it does, it allows us to represent big numbers and very small numbers with very few digits. That's all logarithms are. That's all they are. Common logs. Now, natural logs are kind of different. They're trying to figure out how things vary in nature, right? You understand? So the base they use in natural logs is like 2.73. It's a weird guy. Common logs, though, all it is nothing but 10 raised to some power. That's all it is. Y'all understand that? 10 raised to some power. So in logarithms, the base is always the same. It's always the same. But it's not times 10, it's 10 raised to some power. So what we do in engineering notation or scientific notation, we take a whole number and then we multiply it by 10 raised to some power. And people try to use that X to the Y key on their calculator, but it's not the same. So what scientific notation is, you have a whole number, then you multiply it times 10 raised to some power, right? In dB, we're dealing with the power that 10 is raised to. Okay. So what is attenuation? What is gain and attenuation? And what is a bell and what is a decibel? Most people have heard of the term decibels before, but very few people have heard of the term bells. Not unless you're talking about a church bell or a doorbell. So, okay. Define the difference between gain and attenuation. State the relationship between voltage, current, and power gains. Calculate gains on the inputs and the outputs and convert gains to dB. What is attenuation? What is gain and what is attenuation? So what would you think gain is? Well, it could be. Gain is you get more out than you put in. Huh? Right, but gain, period. Gain is getting more out than you put in. Period. Right? Now, amplifiers give you gain. Amplifiers give you, what type of gain does amplifiers give you? Starts with P. Oh, yeah, that's all an amplifier is designed to do, to give you a power gain. So I get more power out than I get in. So when we get power gain out of an amplifier, if we increase the voltage, we can get a power gain, but we also could get a power gain if we increase the current. Right? You understand that? But you have to understand amplifiers don't create power, they manage power. Y'all understand that? So your radio don't create power. It manages the power coming from your power supply, right? You understand that? A lot of people think amplifiers create power. They don't. You can go out there all day long and try to turn the volume on your radio and try to turn it on, right? You understand, with your battery off, and you don't hear anything. So you got to get that big battery or that big DC power source in there. And all an amplifier does is manage that power. So when you say you get more power out than you put in, then what you put into it is what you're trying to amplify. The power that you get from your amplifier comes from your power supply, right? You'll understand that. So what's attenuation? If gain is getting more out than you put in, then what's attenuation? Lose it. So attenuation would be less out than you get in, right? You understand? And that's what we're fighting against. So all communication cables are going to attenuate the signal. And that's what we're trying to do, right? Gains are calculated as in, there it is. It's all gain. I don't care what kind of gain it is. It's always what? Out over in. So if you get a pay raise, that's what you do. You take out over in, right? That's how they calculate your 3%. We're preaching to get a 2.5% pay raise. So that means if I take my new salary and I divide it by my old salary, I'm going to come up with 2.5%. So what I've done is calculated my gain, right? Luckily, hopefully I'm not going to get a attenuation. You know what they did 2 years ago, right? They gave us a raise and they raised our insurance the same amount as the raise. Gains do not have units. So if I get a 2.5% pay raise, is that $2.5? Is that $2.5 cents? So gains are just multipliers or dividers. So I could take my output and divide it by my gain, and that would tell me what I started with, right? Or I could take my input and multiply it by my gain, and that would tell me my output. If an amplifier has an input of 0.1 volts and an output of 5, what is the voltage gain? I should go through that and pay it. No, it's out over in. It's out over in. 50, yeah, so the voltage gain would be 50. 50 what? 50 volts? Just 50. All it is a multiplier, right? So if I know I have that gain, I can say, okay, if I put 10 volts in, what would be, if I get 10 volts out, what would be my input? Well, I could take 50, I could take that and divide it by my gain and come up with 1 volt, right? You understand that? So gain has no units, but for some reason, people want to put units out there. If I say what would be the voltage gain, they want to say it's got a gain of 50 volts, right? You understand? Fractional gains means that there is a loss in the system because the output is less than the input. So what is the power gain? We still call it a gain, strangely enough, even though it's attenuation. What would be the power gain if the input to the system is 8 watts and the output is 6.56 watts? So what would be my attenuation? Out over in, 8 watts out, 6.56 out, 8 watts in. What would that be? Huh? 0.82, something like, okay. Y'all understand? Is that watts or, no, it's not. It's just a number, right? So now that I know the gain, this gain number, then I can take my input and multiply by that, and that would tell me what my output would be. 50 down here is 0.82. Good. Gains are multipliers and have no units. If you know the gain and the input to the circuit, how can you calculate the output? Just take your input and do what? Multiply it times the gain, right? If you know the gain and the output, how can you calculate the input? Well, you take the output and divide it by the gain, right? Are you okay?
It's going to be tricky to remember which one divides and multiplies. The only thing.
Yeah. A circuit has a voltage gain of 15.5 watts. What will be the output if 12 volts is applied to the input? So a circuit has a voltage gain of 15.5. If I apply 12 volts to the input, what would be on the output? Get that down. Yeah, I think I did pretty good once we put the little triangle up there, right? If a signal passes through a multiple gains, the gains are multiplied together. That's what people don't understand too. You know, I say I've got an amplifier, and this guy here has a gain of 100, and I feed that into an amplifier that's got a gain of 100. What would be my total gain? Huh? Yeah, and a lot of people though will want to add them together. And I say, well, I hope you come to work for me. Right? Because if I double your salary, I mean, if I triple your salary, if you're making $1 and I triple it, you get $3. If I triple it again, you don't get $6, you get what? You get $9. So gains are additive, right? I'm sorry, gains do what? They multiply. So the gain of these two guys would be 100 times 100, right? So here it says the total gain would be, so here's a system we got, and you just multiply them together, even attenuations. So it says 23 feeds into another amplifier that has a gain of 47, feeds into through a conductor that has a gain or attenuation of 0.7, and we just multiply them all together to get our watt. Because it's less than 1. It's actually an attenuation. So if it's got a fractional gain, that means it's actually a loss, right? You understand? If it's got a whole number gain, then it's a true gain. Everybody okay? And then it says what would be the voltage measured on the output of 3 amplifiers if 0.2 volts is fed into the first. So what I would do is I would just do what? Take this, multiply it by the overall gain of the system, and then that'll give me the output. Are you okay? The more complex the gains, the more complex the math. So what would be the overall gain of a system that has the following individual gains? So what would I do? I say 15 times what? 6 times 0.015 times 7.3 times 0.025. And whatever I came up with, that would be the gain of the system. So what we got? Anybody got it yet? I don't know. 24.6. $24.637. Of course, you're going to round it. Are we okay? Fractional gains create an output that is less than the input. This is often referred to as an attenuation. In power and communication media, attenuation is also defined as the loss of signal strength over distance. All media has attenuation. Attenuation is also introduced by splices and termination, which is we're going to learn here, right? So our goal is to not add any attenuation at all when we do our splices. The communication channel consists of multiple devices, has the following power gains. Y'all can do this. I'm just going to go ahead and go through this. That would be a big gain, right? Exponents consist of 2 parts. And what's 2 parts? We don't eat around my computer. In fact, that's college policy. Right? If you're going to drink around the computers, you need to have the keyboard in and not be using my computer. Everybody okay? We let y'all drink even though that's against college policy. I should be recording that. I need to go back and delete that. But no, we don't eat around these computers. You'll never see me eating out here. Fractional gains creates an output that is less than the input. This is often referred to as attenuation. The power and communication media attenuation is defined as the loss of signal strength over distance. So when you start talking about communication media, they're going to start talking about we're going to be allowed a certain amount of dB loss, right? You understand? And if we exceed that dB loss, then that would be a problem. So we're saying these network cables, how far are we supposed to run those things? How far can we run them without running them through like a repeater or something like that? Well, that's the kind of stuff that you need to understand. I think we already looked at this. We looked at this. No, this is communication channel consists of multiple devices, has the following power gains. So you can see when you come up and look at this, the answer is 1,105,444.53. Now, in engineering notation, what would we do? We'd start moving our decimal point over, 1, 2, 3, 4, 5, until we got one digit, right? You understand? One whole number. And then we'd round it. It would say what? We'd say 1 something meg, right? You understand? And why did we do that? Well, as soon as I did that, I rounded, right? You understand? So that means it's not perfect, but it's perfect enough, right? Especially in electronics, because our math is perfect, but our components is not. So in DC, when you were playing around with your resistors, you measured all your resistors. And then you calculated your voltage drops with your measured values because you were trying to prove Ohm's law, right? You understand? So in that, by George, if you measured them and then you did the math, your voltage drops came up to be just about perfect, as accurate as your meter was. After that, we don't do that anymore because we understand that my math is what? My math is perfect, but my components are not. So we understand if I calculate a voltage drop of 10 and I measure 9.6, it's okay, right? You understand? So what we're doing is shooting for range. So because we round these things, you know, as long as we're accurate enough for a system that's not perfectly accurate, right? You understand? Figuring gains using this method requires the use of a calculator. We don't like to calculate. Exponents consist of 2 parts. We have what we call a base. I think they also called it a Nesda or something like that. We'll call it a base. It starts with an M. Why I brought that up is because Siemens PLCs has what they call floating point math, and it deals with exponents, and they call the base something else. It starts with an M, and I can't quite get it. We're going to call it a base. So exponents consist of 2 parts. We have a base, which is x, and then the base, and then a base, and then an exponent that we raise that base up to, right? Y'all understand that? Y'all familiar with this? An exponent indicates the number of times the base is multiplied by itself. What would be the number represented by 5 to the 6? And we'd have people in DC that would say 30. Right? You understand? But what this means is I'm multiplying 5 times itself 6 times, right? So what do y'all come up and get? Pretty big number, right? Yeah, 15,625. Exponents allow very large numbers to be represented with very few digits. So it's a lot better to say 5 to the 6 than to say 15,625, even though they're totally equal, right? You understand that? If the base is the same, the numbers with exponents can be multiplied by simply adding the exponents together. If they have the same base. Right? You understand? So I could come up here and do this. I could say 3,125 times what? 125 equals this. Or I could say 5 plus 3 is equal to 8. And then I could raise 5 to the 8th power. And that would give me the same number, right? You understand that? So what's nice about exponents, when I multiply, all I have to do is just do what? Just add the exponents and then raise my base up to that power. But this only works if the what? If the base is the same. Okay. So we come up and get exactly the same number. Hoping you can add exponents without a calculator, because these are going to be usually whole numbers, right? Logarithms are numbers represented by a constant base. That's all a log is. We have 2 logs. We have what we call a natural log, which is this weird 2.718, but we don't use that. We're going to use common log. Common logs is 10 raised to some power. That's all a common log is. So if you got a log key on your calculator, so if you got the log key to the calculator, what it's going to do you is it's going to give you the exponent. Y'all understand? So if I come up here and bring up my calculator, and here's my log key. Y'all see my log key? Huh? Right here. So I'm going to come up here and enter 100, and I'm going to hit the log of that, and it says 2. So 10 raised to the 2 is 100, right? You understand that? And that's all log is. All a common log is the number that 10 would be raised to. That makes sense. Everybody okay? So if I put what's the log of 1,000? 3. What's the log of 10,000? 4. And that's all log is. It's a constant base. The base is always what? 10 on a common log. And that's what we use in communications. Are we okay? But I can do any number. I could come up here and enter a strange number. And then I can enter the log. And it comes up and gives me an extremely big number. But if I took 10 and raised it to that number right there, it would come back and give me my strange number, right? You understand that? Well, what do you think we're going to do with this big number? We're going to round it, right? You understand that? Going to round it. Now, as soon as I start rounding it, just like we do in engineer notation, it's not going to be perfectly accurate, but it's going to make my math a lot easier, right? You understand? And it's going to be a lot easier to deal with. Now y'all experts. So a common logarithm is 10 raised to some power. The power to which it is raised to is called a bell. So what is the bell for 10 raised to the 5.256 power? 5.26, that's the bells, right? So it'd be this many bells. That would be the bell. That makes sense. So we call that bells, right? Bells. To convert bells to the actual number, all we have to do is raise 10 to that power. In just about every calculator, right beside the log key, guess what's usually right beside the log key? In fact, on a lot of calculators, it's the same key. You hit shift to get the log, or you might hit one key to hit the log, and then the same key you'd use to get 10 raised to that power. So if I come up here and I say 10, then I say, if I say 5.256 and I hit that key right there, it gives me the actual number. If I come over and hit the log key, then it gives me that log, right? You understand? So that's all we have to do to go between log and the actual number is just use these two keys, and they're where? Well, they're right next to each other. They're either on most scientific calculators, they're either different keys. They're right beside each other, or they're what? One of them's got to shift it, or one of them's got to hit a second function, but they're usually the same key because we go between these two, right? Y'all understand? So y'all know what a bell is. What's a bell? That's what 10 is raised to, right? To get that number. Are we okay? Any number can be represented as a common log if enough decimal points are used in the bell. It's close. We're not there yet. We're dealing with bells. We're not dealing with decibels. We're dealing with bells. But you got the right out. Are we okay? Yes or no? Now y'all gonna be experts. So there's the number, right? What will be the actual number of 2.4 bells? 10 raised to the what? 2.4, which is going to be 100 and something. So I can look at that number. If I know powers of 10s, 2 is 100, so it's going to be 100 and something. It's going to be between 100 I know it's going to be between 100 and 1,000. And it's non-linear, guys. So what does it come up and give me? What's that? What's that? 251. But see, right off the bat, I knew it had to be somewhere between 100 and 1,000. I didn't know where it was at, but so, are you okay? Well, yeah, but when we deal with approximations, which we do with electronics, we get a good idea of basically what we're looking for before we get our answer. You're right, it is a large range, and it's nonlinear. And if you dealt with this a long time, you would have a pretty good idea of what it would be, right? You understand? So that's the actual number. Now, of course, we're going to do what? We're going to round this one. Relative to power, decibels are equal to bales times 10. So that's what a dB is. It's decibels times 10. Oh, I'm sorry, it's bales times 10. So how many dB would, and now this is the way we abbreviate dB. We use a lowercase d and an uppercase d. That's why we suppose the decibel. But it's 10 bales, right? You understand that? It's tens of bales. So all we would do is just take this number, and we don't even have to use a calculator. We just shift it to the right one time. And then we call it dB. So instead of saying 5.256 bales, we would say 52.56 dB. So all we have to do to go between bales and decibels, so we move it to the right one time dB, move it to the left for bales, right? Everybody understand? So it'd be 52.56 dB. When gains are represented as dB, the number is usually rounded to none, 1 or 2 decimals. But very seldom you'll see over 2 decimals. I've never seen over 2. I'm not saying you might not run into it, but I've never seen over 2. And that's why we use milli and micro when we start rounding, right? Or kilo. You know, if I come up with 1,253 ohms, we would say 1.3K, right? Or something like that. We would round it, right? You understand that? I think in DC, we require y'all to round to do 2 decimal points. But when you get into like solid state and AC, we drop it down to 1, right? Because it's accurate enough. But we understand that. So we could represent that 52.56. You might see it. You probably won't see 5.25 bales. You'll probably see it 53.53 dB, 52.6 dB, or maybe 52.56 dB. But before you hit that power of 10 key now, you're going to have to divide that by 10, right? Y'all understand that? To get the actual number. Yeah, because when I hit that powers of 10s, that's bales. You understand? So what I'm saying, if I came over here and had a number, so here's the number. So I'm gonna come up here and bring my calculator up. Okay. So the number I'm gonna do it the whole time. So I'm gonna say 5.256, and then I'm gonna come up here and I'm gonna take the log of that. Okay. So that's the actual. That's not right, Rich. I'm not going to take the log of that, Rich. 5.256. Okay, so this is the actual number. Okay, you understand? Okay, but let's say, and so if I hit this key, it comes up to be that. Well, what if I read in something and I say it's 52.6 dB? Well, I'm going to say it's 52.6 dB. And if I hit that key right there, that's screwed. That's not the number. Okay, you understand that? So what I've got to do, if I enter dB, if I say 52.6, then the first thing I'm going to do with my calculator is I'm going to divide that by 10. So what I just did is I took decibels and converted it back into bales. So now I can come up here and hit this key, and that would give me the actual number. So that's just something you're going to have to remember to do. Right? You understand that? So a while ago, I could go directly from the log and then back. But now, if I'm using dB, I'm going to have to take my dB and divide it by what? By 10 to get the actual bales. You okay, Dwayne? Well, if I'm going to use my calculator, I can't. You could rekey it, but it's easier. You got that number up there just to do what? Just divide by 10. You okay? And you're right, I can move it, but we're using our calculator to do a lot of the work for us. That was my glasses that fell off. I thought it was my safety glasses. That's why I didn't pay much attention. Converting to dB allows numbers to be rounded and still maintain some degree of accuracy. So just like when you're using milli and micro and kilo and mega, when you round, you're going to use some degree of accuracy, but you got to understand your electronic components are not accurate anyway, right? You understand that? So convert the following bales to dB. This should be pretty easy. So what would the first one be? 15.6, good. 122.3, right? 1.35, right? 58.56. Are we okay? Are we okay? Scientific calculators have a log key which converts the bales into that. You've also got a 10 raised to some power, right? Are we okay? A system has a gain. And this is what they do. So in communication systems, they're not going to give you a voltage gain. They're not going to give you a current gain. They're going to give you a gain in the system. So if these are gains, 247, 556, 0.34, so this is the attenuation, 45, 6. What I'm going to do is I'm going to take this and convert them all to dB. Now notice if it comes up to be minus, what does that mean? It means it's attenuation, right? You understand? If it comes up to be a positive number, it means it's a gain. So I can just look at this right off the bat and tell if it's a gain or attenuation. Now what I would have to do is if I did this longhand, if I come up and did this, if I did that longhand, then I would come up and get this gain right here. Right? I understand. But if I use dB, the base is all the same. So if I use dB, now let's use dB instead. So if I use dB, all I've got to do is what? This is supposed to be add, guys. I don't know how that ended in there. Oh, I'm sorry. So we would just do this because these are attenuation. So I'd say 23.92 plus what? 27.53 minus. So all I have to do is just enter everything just like my dB is, minus 4.68 plus 16.53 minus 1.74 minus this, and I would come up and get an answer. You could do this without a calculator if it was in what? If it was in dB. Because all you got to do now is what? Add, right? So that gives me an answer of 60.44 dB. Are we okay? Hopefully that's right. Not checking up on that. No, I was just joking because a while ago I didn't know this. And it always surprises me how many times I teach a class and use the same PowerPoints and people don't notice it. So that would be equal to this number right here. So if I took this dB, then what did I do? So it's rounded to 2 decimal points, which gives us some mode of accuracy. So what I do is I shift it over, I raise 10 to that power, and that would be the answer. So this is the actual answer. This is rounded. Now this would be perfect. This right here is perfect enough, right? You understand? But what it gave me the ability to do is to do what? Get a good feel of how the system works without doing all that multiplication. So this is why communication systems, when they start talking about loss, they're going to give it in dB. Right? You understand? Gains, they're going to give in what? dB. So if we're going to deal with communication cables, then we got to understand dB. Are you okay? Even though rounded, dB is still accurate. It's still an accurate approximation of the actual power gain. It is a heck of a lot easier to deal with than multiplying all those little gains, right? Everybody okay? So that's what's nice about this. The base is the same. Back in algebra, you learn if all your exponents have the same base, then all you have to do is add the exponents together and then add your base, that constant base to that power. And that's all log is. So all we do log with, we use logarithms exactly the same way that we use engineer notation. So what do we use engineer notation for? We use engineer notation to represent very large and very big numbers with very few digits. And that's exactly what we use logarithms. And everybody gets scared of them, right? You understand? That's what we use it for. Very simple, right? Well, simple. There you go. Power, but we got to understand something about power too. Power is the rate of work that's being performed. Voltage is different. and electrical potential that causes current to flow. The actual formula for power is what? V is equal to what? P is equal to V times I. But remember also, I is equal to V over R. So if I don't change the resistance of my circuit, and this is what gets people messed up, if I double the voltage to a circuit, what happens to the power delivered to the circuit? So I've got a given circuit, and I double the voltage to that circuit, what happens to the power produced by that circuit? I guarantee it increases. To how much? Huh? Huh? Well, that's what people think. But this is the guy that's going on, Rick. So I'm not changing the R of the circuit. Well, if V is equal, so let's just make up something. So let's say I start off with 2 volts. So current and voltage are directly proportional to each other. So if I come over here and I say, okay, I've got a power in a circuit. So let's say I got 1 amps times 1 volts, that would be 1 watt. But if I come over here and double my voltage, it goes to 2. My current goes to 2, right? You understand? So what did my power go to? 4. And this gets people, you can get people on that all the time. You say I double the voltage to a current, what happens to power? They say, well, it doubles. No, it don't. It goes up 1 watt. 4. Well, if you triple the voltage to a circuit, what does it go to? 9. If you half the voltage to a circuit, what does it do? Quarter. Drops down 1/4. So if it goes down, it's 1 over the square. If it goes up, it's the square. Okay, y'all follow this? Yes or no? So power varies with the square of the voltage. Up is times the square. Down it's 1 over the square, right? If a circuit is 10 volts, 10 amps, what would be the power? We know it's going to be 100 watts. If the voltage circuit is triple, what will the power do? Since the I is equal to V over R, if the voltage triples, the current triples, so it went up to 900 watts. And this is why if you take a 110 light bulb and you put it on a 240 circuit, it pops just like that. Because it tried to produce 400 watts, right? You understand? Or if you got a 100 watt light bulb and you put it on 26 volts AC, it's not even going to glow any, right? You understand that? We do a circuit in motor controls where we simulate multiple loads in series. In motor controls, you can't put multiple loads in series. So if I don't know if you've had motor controls or not, but what we have is we have a light bulb up there and it's dropping voltage and it don't even come on. I've had, well, there's something wrong. This light bulb's not coming on. Well, what's the problem? We got three loads in series. So instead of getting 120 volts, it gets what? I think the relay resistance is like 1,000 ohms, and these guys here are, so if they were 1,000 ohms, then it would get 1/3 of the voltage, right? You understand that? So it would get 1/9 of its power. Y'all understand that? And so if it's a 25 watt light bulb, and you divide that by 9, right? The light don't even come on. And they say, well, something's wrong with this light bulb. It don't come on. I keep telling them, it's not getting a watt. Not getting enough voltage to produce that power. Notice that the power is increased by 3 squared. In communication systems, power systems, we are very concerned with the amount of power delivered to, produced and delivered. Power gain and loss is very difficult to measure because it is voltage times current. Voltage gain and loss is very easy to measure. That's probably one of the two of the 3 meters we have available on our multimeter. Which ones do we use the most of? Which one do we use the most of? Voltage, followed by ohms, resistance, and then amps every once in a while. Very seldom in the field do you use that thing to measure amps. So when I talk about power, we're trying to make it relative to voltage, right? You understand? Because voltage is real easy to measure. If a circuit has 10 volts applied, produces 10 amps in the current flow, what does the power produce? 10 volts, 10 amps is going to be 100 watts. Everybody okay? If the voltage is half, what happens to the power? you say has, it dropped down to 25 watts, right? You know what I'm saying? If half, yeah. So it would drop down a factor of 4, and that's why the light won't even come on. You got a 100-watt light bulb, and you put 25 watts on it, it's not going to do nothing, right? Also, if the voltage halves, the current halves, so the power dropped down to 25 watts. Notice that the power decreased by 1/4. If the voltage applied to a circuit quadruples, what happens to the power? We already know that, right? If power in the circuit triples, what happens to the voltage? If the voltage applied to the circuit halves, so we're okay there. On the previous side, we learned that half the voltage, we get, when the voltage halves, the power decreases by the original, divided by what? 2. Power doubles. Okay. Now this is what comes in. If the circuit produces 25 watts, what happens to the power? No. Everybody okay here, right? Okay. What we're trying to do is we're trying to get to what happens. So what would be, how much would the voltage drop to get half power? Huh? Yeah. So if I had 100 watts, what would it drop to get 50 watts? How much would it drop to get 50 watts? How much would the voltage drop to get 50 watts? Okay. What would be, so here we got 10 amps, 100 watts. What would cause it to triple? We know that. What would cause the power to half? So 10 divided by the square root of 2, square root of 2. So half. So y'all understand it? Square root of 2 to half would be if we divide it by 1.414, then that would give me half. Everybody understand that? That's 7.7. Everybody understand that? We could change division and multiplication by taking the reciprocal of the divisor. So as an example, multiplying 0.707, which is the reciprocal of 1.414, is the same as dividing by 1.4. So the rule is 70.7% of maximum voltage, 0.707, would give you half power. Y'all understand? Let's see how we got that. Yes or no? Well, we use that. You're going to find we use that number a lot. The half power point will always equal to the maximum voltage times 0.707. Fractions can also be expressed as percentage. So if the voltage drops 70.7% of its maximum value, the power decreases by 50% of its maximum. The half power point is usually considered the maximum loss allowed by a medium. So y'all heard of bandwidth. What's bandwidth? Okay, so how do we come up with that right? Well, what they do is they come in here and they look at the maximum output that the system can deliver. So if this is frequency going this way, what happens is down here it's going to attenuate, and then it'll come up and we'll go up here, then we get a maximum value, and then it'll drop down, and then it'll move over. And what we do is and this is power. This is not voltage, this is power. Huh? So what we would do is we go to the half. So if this is 100 watts, then the cutoff of frequencies would be 50 watts. And over here, this would be 50 watts. And the bandwidth would be that range of frequencies between 50 and 50. But this is what? This is power. Everybody understand that? Now, power gain. So power gain would be equal to power out over power in. Everybody understand that? Everybody understand that? Now, if I wanted to go to dB, we'd say dB would be equal, and this is the way we say it, guys, so you just have to get used to it. We call it 10 log P out over P in. This gives me the power gain. So, but you got to do this backwards. This is the way they give you the formula, but you got to do it backwards. So what would we do first? We'd take power out over power in. Then we would take the what? The log of that. And then we would do what? Then multiply it by 10. So that's the way they give the log formulas for power. That's the way they'll say it. They'll say power gain in dB would be equal to what? We say 10 log P out over P. Okay, we're okay. But that's power. We want to get this relative to what? We want to get this relative to voltage. Yeah, so that would be, if my power gain was 100, right, and my input power was 10, and my power gain would be 100 divided by 10, then I would take the log of that, and then I would multiply that by 10, and that would be my dB. Okay, you understand that? Yes or no? But when they give you the formula, they give it to you back, because it just flows better. So they say power gain in dB would be 10 log P out over P. Well, actually, normally you might see this sometimes. dB is equal to 10 log AP. So A is another way that they represent gain. So you might see that at one point. What's gain? Gain is out over N, right? So you might see it listed like this. So A in a formula like this would be the gain. Are we okay? That would be P out over P. Huh? No, this is just power gain of an amplifier. Huh? Yeah, we're talking about the gain of a system. We're not talking about power transmission. We're talking about the gain of the system. Alabama Power does not give us power gain. Alabama Power gives us power. We run that through an amplifier. We run that through a communication system. We're going to get some kind of gain out of it. We're either going to get a positive gain or we're going to get a negative gain, right? Now, what we're trying to do in amplifiers is we're trying to get one type of gain out of an amplifier. What kind of gain are we trying to get out of an amplifier? Starts with P, guys. Power. That's what we're trying to do. We're trying to get power gain. Power gain. But if I was going to get the power gain, I would have to measure the power in and I would have to measure the power out. Right? You understand that? What's the problem with measuring power in and power out? Well, when I measure power in and power out, I would have to measure current and I would have to measure voltage. So I'd have to break my circuit and I'd have to measure that. I would rather have a way of representing power gain if I could measure voltage in and voltage out. Right? You understand? If I could measure voltage out and voltage in, if there was some way I could figure power gain relative to voltage, then that would be great. Power varies with the square of the voltage. With the square of the voltage. So if I go to 20 instead of 10, this is squaring the voltage. That's power. So what I can do is I can measure V out over V in. I take the log, instead of multiplying it by 10, I multiply it by 20, and it gives me the power gain. It don't give me the voltage gain, it gives me the power gain. Without ever measuring what? Y'all understand? So if I measure my voltage in and my voltage out, power varies with the square of the voltage. Well, it's the square of the number. So if I come over here and I go 10 to the first, and then I go 10 to the second, that would be just like me squaring it, right? You understand? So what's 10 squared? 200, right? Understand? If I squared this, it's going to be 10 to the fourth, right? You understand? So that's what I'm saying. If I take my V out and V in, instead of using 10, I use 20, That's squaring the voltage. You understand? Yes or no? Well,
It looked like you.
well, you're not doubling it. It's a power of 10. So if I go from 2 to the first to 2 to the second, am I doubling? So if I go from 2 to the first to 2 to the 2 squared, so that would be what this is, right? Because this represents this right here. Okay, you understand? So what I do when I multiply by 10, I'm using the actual number. If I multiply by 20, I'm squaring that number, right? You understand? Because you got to represent it. You think about bells. So if I go from 1 bell to 2 bells, I've squared the number, right? You understand? Power varies with the square of the number, with the square of the voltage. So if I take my output voltage and I square that, and I got my input voltage, I square that, and I take that, right? You understand? Then I end up with the power gain. So I'm getting this much more voltage out, right? You understand? So that's all we're doing. So we can figure the power gain of a system without measuring current. I can measure my output voltage. I can divide it by my input voltage. I can take the log of that, and then I square it by multiplying by what? 20. So we just squared the voltage, right? You understand that? Which is what the power is. Power varies with the square of the voltage, right? So we could do all this calculating. I could come up on a circuit and I can say, okay, I'm going to bring 10 volts into 100 ohms, and I'm going to get 100 volts out into 100 ohms. And I could go through all that math. I could calculate all my current. I could calculate every bit of that, but I could take 100 divided by 10, take the log of that and square it, and I'd get exactly the same answer. So I could calculate the power. How would I calculate the power? I could use V squared over R here. I could use V squared over R. So let's do that. So let's say this is 100 ohms. And let's say this is 100 ohms. So what would my power in be? So I'd calculate all this stuff. Well, I'd say V squared. So it'd be 100, right, divided by R. Okay. So what would that give me? Over here, so this would be what? 100 divided by 100, so I get 1 watt in, right? You understand? Okay. Over here, this is going to be 100 squared, which is going to be 1,000 divided by 100. What's that going to give me? That's going to give me 10 watts out. Okay. Y'all understand that? So what did I have to do there? I had to do all that calculating, right? So okay. But I can come over here and I can say, what's my voltage out? 100, right? Divided by what's my voltage in? 200. I take the log of that, right? And then I multiply that by 10. So that means I would get a 10 dB power gain. Is that what I got? Right? But what I did is I said 100 volts and 10 volts, and I came up and got exactly the same answer. You see that? So what I did is I measured my voltage and I squared both of them because power varies with the what? With the square. So that's for the formula. So what I can do now, instead of measuring current, instead of measuring power, if I take my output voltage divided by my input voltage, right? Take the log of that, multiply it by 20. What did it give me? It gave me my power. Ain't that cool? Charles, you still look huh? Yeah. So what we did is we did all that math over here. Right, you understand? So I came over here, I got 1 watt in, I got what? 100 watts out. That's still not right. Okay, then I took my output power, I divided by my input power, my output divided by my input. That's wrong, Rich. It's 100. It's 100 divided by 10. So that would be give me what? Huh? Okay, so that's going to give me 10, right? You understand? And then we did it with voltage and came up with what? 10, right? You understand? So, but the formula changes. So if I want to use voltage and I'm using dB, then we're going to use what? V out over V in 20 log V out over V in. And what that's going to do is it's going to tell me the power gain in the circuit. Well, and I don't have to measure power. I don't have to measure power. I can measure my output voltage. I can measure my input voltage. Take my output, divide it by my input, and then take the log of that and multiply it by 20. And I don't have to measure power. Y'all understand? That makes sense? Huh? Slowly? 30 log's nothing. We don't vary, but the voltage don't vary with the 30. The voltage varies, power varies with the square of the voltage. Now I could say current, so if I could measure my current, then my power gain would be equal to, my power gain, AP, would be equal to 20 log I out over I in. Because power varies with the square of the current, because if the current squared, it means what at the square? The voltage. 30 log is nothing. I mean, I don't know what that is. So what we're doing with 20 log is we're squaring the voltage. And I know that my power varies with the square of the voltage. So that's all you're doing with 20 log. So we could say, if I measured the output current and I measured the input current, I could take my output current, divide it by my input current, right? I could take the log of that, I could multiply it by 20, and it would give me my power gain.
What's the 10 log?
The 10 log is power. But that's power out over power in. But the problem is, to get power out over our power in, I've got to measure power. How do you measure power? Without having to measure power. How do you measure power? How do you measure power? How does your power meter on your house work? Well, it's measuring current and voltage. So to measure power, you would have to measure current and you would have to measure voltage. Right? But I don't have to do that. I mean, I can measure my output voltage, I can measure my input voltage, and instead of using 10 log, which is what I use for power, I use 20 log, and that gives me the power gain. Ain't that slick? Huh? But it's got to be in a system that's got impedance matching. So over here I can't go, and this is why we use them in communication system, because we have impedance matching. So I can't have 100 ohm here and 1,000 ohm there. The formula's gone out. So notice on both these I used what? 100 ohms and 100 ohms. Now it don't work if the impedances are different. But in communication systems, your impedances are going to match, right? You understand? They match those impedances so we can get maximum transfer. So your cable is 50 ohm cable. The input to your cable box is a 50 ohm input. All the amplifiers that they use are 50 ohm amplifiers. And so what they do is they match, so that means 50 in, 50 out. Now this will work. It wouldn't work if I said 100 in and 10,000 out, right? Because now my current would be different on my output. So I wouldn't get the same current gain, right? Does that make sense? You're matching it to 300. So you got a 300 ohm antenna. Well, it don't match to a 50 ohm input. So you put that little impedance matching transformer on there, and that converts it over from what? From 300. So on this side it's matched to 300 on that little impedance matching transformer. The other side is matched to 50. And you couple through a transformer. That's all that is. It's nothing but a transformer. But on this side, those windings have 300 ohms on impedance. The output, the secondary, has 50 ohms worth of impedance, so you're matching to a transformer. And we call that's exactly, they're not in there to give us voltage gain, they're not in there to give us power gain, it's in there to convert, 300 ohm over to what? 50. And you could figure that out. I mean, so that's a really good point. So you put that little thing in there, right? And that's all it was, just a little what? Impedance matching transformer. And you went from like the twinplex or the 300 ohm over to the coax. The flat, yeah. And why are those things spaced out perfectly? Why can't you just use 2 wires? Well, no, the impedance. So you're setting up a capacitor between those 2 wires set up by that piece of plastic. So that thing is perfectly spaced. I mean, you can't go out there and say, well, why can't I just run a regular wire? All I need is 2. I've seen people, all I need is 2 wires. Yeah, and you brought it into the back of your TV and it put out and everything was matched, right? You understand? But the problem is we went from that twin plex cable over to coax. And like you said, if you're using that old antenna, that's fine. That's going to pick up everything. That sucker even picks up what? These. It's your TV that filters them out. So all you had to do is convert it from what? A 300 ohm system over to what? A 50 ohm system, and now you got impedance matching. So now you understand. Well, what would happen if you just run regular house? If you went out and bought a big old long extension cord at Lowe's and hooked that up to the screws on your antenna and run that into, you'd get a crummy picture because what did you do? You screwed up the impedance matching, right? So now you understand it. But if you can measure, of course, you'd have loss. So if you can measure your output of your antenna and the input of your TV, and then measure it with voltage, then you would get the loss of your cable come down to there, and it would give you the power loss, right? That makes sense. But you have to measure it on the 50 ohm side. So you measure it on the 50 ohm side, and then at your TV, that would still be on the 50 ohm side, and you could calculate, huh? Where you screw the coax in. Are we okay? So what we're going to do is we're going to get dB losses all the time, and this is what they're going to say. So it says half power point occurs at 70.7% of the maximum voltage, converting either to power gain. So this is power. So notice what I did. So I just said 70.7% of the voltage. I took the log of that, and it gave me minus 3 dB. I took a dB loss of 50%, right? So so here I had a gain of 70.7, right? Which was attenuation. Here I had a 50% gain of power, right? Which is half power. And both of them came up to be what? Minus 3 dB. So you'll see a lot of people talk about the cutoff frequencies, and they'll say at minus 3 dB. And of course, what are they talking about? Are they talking about voltage or are they talking about power? They're talking about both of them. It's just if I measured my voltage would be 70.7%, which gives me a minus 3 dB power loss, right? Okay, so this is the way they do. So you'll see a lot of people, so when we get into a lot of cables, they'll say a maximum loss of 3 dB. They don't put minus, they don't say a minus 3 dB, but they'll say a maximum loss of 3 dB. And of course, if they say a maximum loss of 3 dB, you know it's a minus 3 dB, right? So that would be, if I was measuring voltage, that would be 70.7 or 0.707 if I'm measuring power, which I don't measure because power is so hard to measure. So minus 3 dB is 50% power. So you'll see that a lot. We'll start looking when we get into our fiber optics. They'll say your loss per pair, maximum loss per pair, maximum loss, and you'll see in communications you're going to see dB a lot. That makes sense? But see how they come up with that minus 3 dB? Ain't that slick? So if you did this on your calculator, if you took 0.707, you took the log of that, and then you multiply that by 20, you're going to come up and get minus 3, or close to it. It's not actually 0.707, it's actually the reciprocal square root of 2. So it's a longer number, right? So I think the reciprocal square root of 2 is 1.41414141414. But we leave off at 0.707. dBm is a little different. We deal with this. dBm is relative to 1 milliwatt. In audio systems, 0 dBm would be equal to 70.7 volts into 600 ohms. So dBm is reference to 1 milliwatt. So 1 milliwatt would be your input, would always be your input. So what they're doing here is they're going to give you an input of a constant input to get your output. We call this dBm. So if you ever see dBm, it's relative to watt. 1 milliwatt, right? Are we okay? And I think that's it for that. So y'all guys go take another break, and then we'll get back and we'll start working on what we're going to do on our next lab, or we're going to start doing on our next lab. Yeah. But you understand now, so all you're doing, remember it's dB. So if I put 2, it would be squared it. But if I use 20, then we're converting to dB, right? And we don't measure. I've never seen, the current formula would be the same. It would be 20 log, it would be 20 log I out over I in, but we don't very seldom use that because what do we have to do with current? Have to break it. But it's so neat that we can measure voltages and calculate a power gain without having anything to do with current. But this has got to be in a system where the impedance matches, right? Y'all understand that? So we can't use this in amplifiers. Because amplifiers, the output impedance will usually always be more or less than the input impedance. So we can't use the 20 log thing in amplifiers. But we can definitely use it in. Yeah, what you got to understand though is you can't measure the impedance of a speaker with an ohm meter. It'll always measure less. So if you got an 8 ohm speaker, it's probably going to measure 4 or 5 ohms because that's an impedance. An impedance has to have a frequency on it, right? So 8 ohms would be 1,000 hertz. Very seldom does it measure. Usually it always measures less. Because that 8 ohms is an impedance. It's not a resistance, it's an impedance. But speakers have a lot of wires in them. So usually it'll always, like I said, if you got an 8 ohm speaker and you measure it with an ohm meter, it'll probably measure 5 or 6 ohms. Because that 8 ohms is at 1,000 hertz. So if your frequency goes up, its opposition goes up. If your frequency, because speakers are nothing but big old inductors. So that's why you try to, instead of trying to let one speaker do all the work, that's why you split it up in multiple speakers. So you have tweeters that are designed, you have 8 ohms at a higher frequency, right? Yeah. Well, doing it with one speaker, they try to resonate with, I don't know if you've ever seen speakers, but you'll have I know y'all going to break. But a multi-frequency speaker will come up and it'll have these little ridges. It'll be solid, and it'll have these little ridges, and it'll be solid. Well, this resonates with a certain frequency. So what happens, this would be out here, this would be your Y one, this would be the bass out here. And this right here might be your mid-range. And then you would have another little section here, and this might be your highs. But what you got is, if you look at it, the spacing between those little ridges are different. So the lengths are set by the wavelength of those frequencies. So different parts of your speakers are moving all at the same time. So that's why it's better to get like tweeters, use the crossover, have tweeters and mid-range. So most of your mute stereos actually give you 3 outputs. They give you a mid-range, they give you a bass, and they give you a bass. In the old days, you had one speaker output on the car, or on the what do they call it, panel like this, on your back seat.
Yeah, well, lay up there.
Yeah, you used to lay up there. Well, that's when they used to let us all ride back a pickup truck too. Now I think it's against the law for kids riding back a pickup truck. Yeah, it's good. We're gonna solve it. So we're gonna look at splicing, terminating, splicing, that's what we solve. You need something? That's our next lab. I've already done it. So you've got two options. You've got the robot who's like mode man does a little different. So it's not actually a circle, it's R. Call it a circle. If I'm gonna do an R, like this, I gotta identify 3 points. Right here. Now, we call this P1, P2, P3. Robots do it different. Like the Motor Man, you have to teach the Fanuc and the other robots, that would be your first point. So wherever you're at, that would be P1. So, understand. So, you gotta teach what? You gotta teach 2 additional points.
Okay.
So as soon as you hit circular move, it's ready to teach this point and that point there. Okay, you understand? Which is fine. That's what it happened. That's what it popped out of. So this one, your entry point would be the last one you teach. So if you come in here with a linear move, you come in here, you stop it. You can say circle move. It pops in 2 points. You have one, you have the other. On the Motor Man robot, I don't care how you get to point 1. You got to teach point 1. So on the Motor Man robot, you got to teach all 3 points. And I think that's the only one I like. I think the ABD uses P1 as your entry. However you get to that point, and then your other 2 points.
Now, if I don't use circle move, but I use like a linear.
Yeah, you could. Well, what you do?
Fine.
Well, no, you wouldn't use fine. It depends on what you want to do.
I want the architectural move.
Okay, then that's what you do. So what you do is you teach a point here, and you teach a point where it levels out, and you teach a point somewhere out here. Yeah, and then you tell it to cut the corner. You tell it to cut the corner between this corner and that. Okay, understand. So it's a little, you have to play around with it a little bit. And then, of course, what would happen is you tell it to cut the corner, and then it's going to cut the corner. It's not going to stop at that one. So if he's using a fine move, it would do that. Right? You tell it to cut the corner. So in the write-up I don't call it, I call it round off. That's what it is. You round off this point right here. Yeah, you can make it fun. Just play around with that. The teams and stuff like that. But you need to teach the point somewhere out in here, right? In fact, I wouldn't teach it too far. It's a narrow arc.
It's not bad.
But I would teach it outside of it a little bit, right? Or you got another option. You can just teach a bunch of points.
Right.
And then you can use very little round off. You can teach them along. You can teach them along the line.
If I use 100,
That's maximum.
that's like,
Yeah, that's really.
all right.
And also, like what I was about that one is you got all the different spaces between 0 and 100.
You got a lot of
Like I said, Motor Man will get 6. I don't know how big. I can't remember how big you get to ABD. There's a lot. But it's called a zone. You got to play around. Of course, if you delegate it a lot, you can learn those zones. I don't know the zones. I just know zone 1 is pretty close to fine. Zone 100.
All right, let's answer.
Cougar's really good too. It's got what's called accuracy. And it's got fine. So it's sort of like the did it again, guys. You know what I do all the time.